Let's look at some global atmospheric effects of volcanic eruptions. Benjamin Franklin was the first to connect volcanism and atmospheric effects. In 1784, he made a connection between a dry fog that descended on Europe and didn't dissipate as the day wore on, and eruptions in Iceland. The 1883 eruption of Krakatoa also had a major impact. Orange skies resulting from ash in the atmosphere reached far from that volcano. And digging through historical documents reveals mention of severe climate hardships in China around the time of the eruption of Santorini in about 1620 AD. The 1815 eruption of Tambora resulted in 3 days of total darkness within a 200-mile radius of the eruption, and 1816 became known as the year without a summer in Europe. Average temperatures fell 1 to 2.5 degrees Celsius below normal throughout New England and Western Europe, and globally, temperatures fell 0.4 to 0.7 degrees Celsius. Crop failures, famine, and disease that are probably linked to the famine affected many areas on Earth, but little knowledge of the eruption existed in the general population. Certainly, these large eruptions that we've discussed before, the Long Valley eruption, Yellowstone, Crater Lake, had major atmospheric effects, but we don't have a historical record of those. So we can look at the 1991 eruption of Pinatubo as an example of the atmospheric effects that result from large eruptions. And I'll mention several of these other eruptions as we go through these slides. The results of the 1883 eruption of Krakatoa are recorded even in Edvard Munch's The Scream, where he depicts the sky over Oslo in 1883 as having this orange glow. This is probably a result of the ash suspended in the atmosphere that migrated around the globe and reached far to the north. We can see Krakatoa in Indonesia is a long distance from Oslo, Norway, where Edvard Munch was painting The Scream. This was a caldera-forming event, and we only have the remnants of that prior volcano. Now let's look at some of the effects of the June 1991 eruption of Mount Pinatubo in the Philippines. On the left, you can see the ash plume as it rises out of the volcano, and on the right is the red haze that results from ash particles suspended in the atmosphere. This space shuttle photo also shows the dark layer above the red haze that is the aerosol layer high above cumulonimbus cloud tops. The aerosol being distinct and separate from ash particles that might be in the atmosphere. In the 24 hours or so following that eruption, the ash cloud and aerosol layer migrated to the southwest from Pinatubo across Southeast Asia. And within about 2 weeks after the eruption, the aerosol had spread around the globe in the equatorial regions. The Observatory at Mauna that studies atmospheric transmission of solar radiation saw a distinct drop in radiation following the Pinatubo eruption. And this is the same kind of decrease in solar radiation seen after other volcanic eruptions, and El Chichon had an even larger effect. Global temperatures, too, drop after large eruptions. And after that June 1991 eruption, there was a distinct drop-off in global temperatures. That temperature drop-off was about 0.4 degrees Celsius globally. satellite instrumentation that monitors aerosols saw an increase in aerosols, particularly around the equator, right after the eruption in the first 5 weeks. That was clearly absent prior to that Pinatubo eruption. Within 4 months after the eruption, the aerosol layer around the equator persisted and had begun to spread toward the poles. A full 6 months after the eruption, we see that the aerosols are starting to dissipate, but it's still not back down to this background level prior to the eruption. This graph shows global temperatures before and after major eruptions, and average global temperatures are shown with the blue line. Areas in the graph above the blue line represent increases in temperature. Areas below the blue line represent decreases in temperature. And what you see are, in addition to Pinatubo, El Chichon and Krakatoa show decreases following the eruption of 0.4, 0.5 degrees Celsius that are clearly different from the pre-eruption temperatures. We can look at the amount of sulfur dioxide, here shown in kilotons, that is released during major eruptions. And we see that Pinatubo, we had over 10,000 kilotons of sulfur dioxide released. That's more than El Chichon and other recognizable eruptions. If we plot magma volume against sulfur dioxide emissions, we see that there's a correlation for both andesitic and rhyolitic volcanoes. We can also measure acid concentrations in ice cores, and in this case it's in Greenland ice cores. And a large eruption of the Laki volcano in Iceland in the late 1700s shows a significant increase in acidity in those ice cores following that large eruption that impacted Europe most heavily. And that increase in acid concentrations also corresponds to cooling following the eruption. This plot shows acid concentrations over time from 1500 to 1970 or so. And what we see are, again, increases in acid concentrations in these Greenland ice cores from Laki, from Tambora, and Krakatoa, and other recognizable volcanoes. In addition to ice cores from Greenland, there are frost rings in trees that we use to see those global temperature decreases, and mainly these are bristlecone pines in California. If we look at the locations of volcanoes, we'll see that 2/3 of all volcanoes are in the northern hemisphere, and only 18% occur between 10 degrees south and the South Pole. And correspondingly, of those northern hemisphere volcanoes, they are volcanoes that have very large eruptions reaching into the stratosphere. So volcanic gas and ash mainly affects the climate of the northern hemisphere. This diagram shows a volcano erupting with its eruption column and plume developing above the cone and rising into this umbrella region that we discussed before. Most eruption clouds stop rising at the tropopause, at the bottom of the stratosphere, and that's where air temperature begins to increase. We see that the ash and gases are dispersed by wind, and that there are reactions taking place within that eruption cloud, converting the sulfur dioxide to sulfuric acid. We see also that that cloud blocks radiation from the Earth, as well as solar radiation, and the ash and aerosol layer can work to increase the planet's albedo and thus decrease global temperatures. All of this is taking place in a zone where the ozone exists and can cause the destruction of ozone. Ash in the stratosphere remains for several months, and sulfur dioxide oxidizes within about a month to produce sulfuric acid, which together with water vapor creates a sulfate aerosol. And stratospheric aerosol can remain at elevated levels for several years after an eruption. Eruptions place ash and magmatic gases into the atmosphere, and the major gases are carbon dioxide, water, and to a lesser extent sulfur dioxide, H2S, carbon monoxide, hydrochloric acid, and other acids. Sulfur dioxide is the gas that causes a major atmospheric impact, and most others are removed through interactions in the troposphere. Temperatures decrease from the surface to the tropopause, which is located about 18 kilometers above Earth's surface. The ozone layer heats up the atmosphere by absorption of UV radiation, and temperature increases up to the stratopause, located about 50 kilometers. Then temperature decreases to a minimum at the mesopause. The reversal in temperature at the tropopause acts as a lid to most of Earth's cloud systems, as well as volcanic plumes. Aerosol layers that are several kilometers thick form continuous veils at heights of 20 to 30 kilometers. Volcanic plumes that do not penetrate into the tropopause have little consequence in terms of global atmospheric effects. Volcanic plumes that do penetrate the tropopause can have a profound impact because particles can remain in the atmosphere for years. In the stratosphere, sulfur dioxide oxidizes to become sulfuric acid, and that process takes about 1 month. Combines with water vapor to form stratospheric sulfate aerosols. An aerosol is a suspension of fine liquid or solid particles in air and includes fog, smoke, and stratospheric sulfate. Aerosols have an impact on the temperature of the planet, and chemical reactions between gases and aerosols can activate anthropogenic chlorine, which impacts the ozone. This plot shows global optical depth. Optical depth is a measure of the cumulative attenuation of electromagnetic radiation when it passes through Earth's atmosphere. So how the electromagnetic radiation decreases steadily as it passes through Earth's atmosphere. The optical depth increases with an increase in the mass of aerosol particles. And what we see is that the optical depth is increasing after major eruptions. Krakatoa, Katmai, El Chichon, Pinatubo. For the Agung, El Chichon, and Pinatubo eruptions, research shows that lower stratospheric temperature increased by about 2 degrees in the tropics and lasted for up to 2 years. And whether we see heating or cooling of the Earth depends on the particle size it's erupted. For the warming effect to overcome the cooling effect, the particles have to be larger than about 2 microns. Pinatubo caused average particle size to increase from 0.3 to about 1 micron, and the result was a net cooling effect on Earth. In general, large particles in the troposphere cannot be maintained for long periods of time, so periods of extended temperature increase are not very common. Larger eruptions don't necessarily lead to larger temperature anomalies, and the reason is that an increased output of sulfuric acid, etc., that can lead to larger aerosol particles. These larger particles have a shorter residence time in the atmosphere, and they also have different radiative properties, for example, the optical depth, so they may not be associated with larger temperature variations.